part of the chapter, that is redox reactions. In this today we will see about the balancing of redox reactions and some of the applications of redox reactions. Now, balancing of redox reactions. In our last video we have seen about the types of redox reactions like combination, decomposition, displacement, disproportionation. Now let's see the balancing of redox reaction. The two methods are used to balance chemical equations for redox processes. One of this method is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on splitting of the redox reaction into two half reactions, one involving oxidation and the other involving reductions. Now basically simple reaction, when we balance it is easier because you have to just calculate the number of atoms present there and you have to balance it on the both sides. But in case of redox reactions, there is an oxidation reduction takes place. There is a transfer of electrons that is taking place. Now in this case, there are two methods which are given on basis of which the redox reactions are balanced. Now first method is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on the splitting of reactions. Okay, so first one, it is basically based on the oxidation number of reducing agent and the oxidizing agent, whereas in the second method you have to split the reaction into oxidation and reduction and then you have to balance them. Now both these methods are in use and choice of their use rests with the individual using them. Now, both these methods are used and it depends on the person who is doing the balancing, whether which method he will be applying, first method or second method, whichever is convenient for that person. So it depends on an individual to use the method. First, let's see the method with oxidation number, okay, or the oxidation number method. In writing equations for oxidation reduction reactions, just as for the other reactions, the composition and formulas must be known for the substances that react and for the products that are formed. So in any case, okay, in general, if you are writing the or you are balancing any reaction, okay, you should know the equation, okay, equation for both. In this case, you have to know the equation reaction for both oxidation as well as reduction reactions. Okay, if you know the composition formula of the reactant as well as the products formed, you can easily balance them. The oxidation number method is now best illustrated in the following steps. Now each step by step we will see the oxidation number method. Now first step is simple. You have to write the correct formula of reactant and product. What are the reactants and what are the products? You have to write the formula correctly. Now in second step, identify atoms which undergo change in oxidation number in the reaction by assigning the oxidation number to all the elements in the reaction. Now, once you write the correct formula, then you have to identify who is undergoing oxidation, who is undergoing reduction. So, if you know who is undergoing oxidation and who is undergoing reduction, you have to assign the oxidation number to that element. Now, how? Third step is what mentions how you will assign them. Now calculate the increase or decrease in oxidation number per atom and for entire molecule or ion which it occurs. Now you have to calculate the increase or decrease in oxidation number for each atom and for the overall molecule or ion. Now if these are not equal, then multiply by suitable number so that these become equal. If you find that they are not equal, then multiply that oxidation number with a suitable number to make the numbers equal. If you realize that two substances are reduced and nothing is oxidized or vice versa, something is wrong. Either the formula of reactant or the product are wrong, or the oxidation number has not been assigned properly. Now, in this case, when you write the formula correctly, you started assigning oxidation number. In this process, if you find that the substances that are reduced, okay, there is a reduction process which is taking place, but there is no oxidation that is taking place, or vice versa. Oxidation is there, reduction is not there. In this case, there is something wrong. Okay, either you have written the formula of reactant or product incorrectly or wrongly, or you have assigned a wrong oxidation number to the formulas or to the reactant or product. So you have to check them correctly. if there is oxidation, there should be a reduction that is taking place. But if there is oxidation and reduction, but the oxidation number varies, then it is okay. You can multiply it with suitable number to make them equal. Now, fourth step is ascertain the involvement of ions if the reaction is taking place in water. Add H plus or OH minus ions to the expression on the appropriate side so that the total ionic charge of the reactant and products are equal. Now, if the reaction is taking place in water, okay, if it is taking place in water, there should be involvement of hydrogen and OH minus ions, right? Hydrogen being positive, you know where hydrogen will be gained and where hydrogen will be lost. So in that process, you have to place the hydrogen molecule and OH minus molecule appropriately on the side which it is required. If hydrogen is on the reactant side, then you have to place it on reactant side. If it is on the product side, you have to place it on the product side, so that the total ionic charge of the reactant and the product are equal. If the reaction is carried out in acidic solution, use H plus ions in the equation. If it is in basic solution, use OH minus ions. If water, then you have to either use H plus or OH minus ions. But if you have a acidic solution, then you have to use an H plus ion. If you have a basic solution, then you have to use an OH minus ions. Okay. Now, next step is make the numbers of hydrogen atom in the expression on the two sides equal by adding water molecules to the reactant or product. Now, if you have hydrogens present in reactant side and you want to balance it in your product side, then you have to add appropriate number of water molecules in the both sides. Okay. And then you have to balance the number of hydrogens on the reactant or product side. Now, also check the number of oxygen atoms. If there are the same number of oxygen atoms in the reactants and products, the equation then represents the balanced redox reaction. So in short, if there is oxygen involved, then the number of oxygen on the right hand side and the number of oxygen on the left hand side should equal. Okay, if the number of oxygen is equal on both of the sides, then the redox reaction is said to be balanced. Okay, let us now explain the steps involved in the method with help of few problems. Okay, now I will explain this with one problem. Now, write the net ionic equation for the reaction potassium dichromate, that is K2Cr2O7, with sodium sulfide Na2SO3 in acidic solution to give chromium ion and sulfate ion. This is the reaction they have described here. You have to react potassium dichromate with sodium sulfate in acidic solution, and as a product you will get chromium ion and sulfate ion. Okay, so this is what the skeletal reaction looks like. Okay, first step is you have to write the skeletal reaction. You have potassium dichromate, you have sodium sulfate, you get chromium ion and sulfate ion. Now assign the oxidation number for chromium and sulfate. Okay, now you have to assign the oxidation number. How you will assign the oxidation number? Here chromium 3 is given in the bracket. So that means your chromium ion has a +3 charge. Okay, your sulfate ion has +6 and -2. Whereas your chromium ion has +6 and -2. Your sulfate ion here has a +4 and -2. This indicates that the dichromate ion is oxidant and the sulfate ion is your reductant. Okay, why dichromate ion is your oxidant? From +6 it has converted to +3, and sulfate ion from +4 -2 to +6 -2. So this is reductant and this is oxidant. Now calculate the increase and decrease of the oxidation number and make them equal. From step 2 we can notice that there is change in oxidation state of chromium and sulfur. So oxidation state of chromium changes from +6 to +3 as I showed you. There is decrease in +3 in oxidation state of chromium on right hand side of equation. Yes or no? Here chromium had changed from +6 to +3 and sulfate has changed from +4 to +6. Okay, now you have to calculate the overall net charge. Okay, in this case what will happen? So there is an increase of +2 in the oxidation state of sulfur ion on the right hand side. To increase the decrease of oxidation state equal, place number 2 before chromium ion on right hand side and the numeral 3 before sulfate ion on the left hand side, and balance the chromium and sulfur atoms on the both of the sides of the equation. Now similarly, how we calculate the numbers? Here you have 2 chromium, here you have 1 chromium. Similarly you have to do, here you have 2 chromiums, so multiply the chromium with 2. So +3 of chromium 1 and +3 of chromium 2, +6 satisfied. Now next is your sulfur. Okay, on the both of the sides you have to multiply the sulfur with 3. Okay, what will happen if you multiply the sulfur with 3? Your sulfur will get balanced. Okay, now as a reaction occurs in acidic medium and further the ionic charges are not equal on both the sides, add 8 H plus ions on the left to make ionic charges equal. Now in the problem I have told you that it takes place in acidic medium. Acidic medium means you have to add H plus ions. Now on the both of the sides there is inequality in ionic charges. So by adding 8 electrons on the reactant side, you are balancing the ionic charges. Now finally count the hydrogen atoms and appropriate number of water molecules on the right to achieve balanced redox reaction. Now count the number of hydrogen atoms and you have to add appropriate number of water molecules towards your right hand side to balance the hydrogen atoms. Hence you will balance the overall reaction. So 8 electrons, 8 water molecules, 8 hydrogen molecules, so 4 water molecules, because 4 into 2, 8. So 8 hydrogen molecules are there. So similarly one more problem is given here. You can go through the problem later. The next one is your half reaction method. First we have seen oxidation number method. Now next one is your half reaction method. Now in this method the two half equations are balanced separately and then added together to give balanced equation. Now in this method what happens? You have two half equations. They are balanced separately and then added together. Now suppose we balance the equation showing oxidation of Fe2 plus ions to Fe3 plus ions by dichromate ions in acidic medium. Okay, wherein Cr2O7 ions reduced to Cr3 plus ions. Now here they have taken an example of oxidation of iron or ferrous to ferric and reduction of dichromate, chromate 6 plus to chromium 3 plus ions. Now you have to balance them separately. Now first step is produce the unbalanced equation for the ionic form. Now first you have to write the entire equation. Okay, you have Fe2 plus Cr2O7 2 minus, giving you Fe3 plus and Cr3 plus. This is your entire equation. Now step 2 is you have to differentiate them into half reactions, oxidation half and reduction half. Now oxidation takes place in Fe because it is converted from +2 to +3, and reduction takes place in chromium because it is converted from +6 to +3. Okay, it is reduced and here iron is oxidized. Okay, now we have separated oxidation half and reduction half. Now balance the atoms other than oxygen and hydrogen in each half reaction individually. Here the oxidation half reaction is already balanced with respect to Fe ions. For the reduction half reaction we multiply chromium by 2 to balance the chromium atom. Now Fe it is balanced. For chromium we have to balance them by multiplying 2 to the right hand side because this is +6, right? If I multiply 2, so +3 plus 3, you get +6. Okay, now for reactions occurring in the acidic medium and add H2O to balance the oxygen atom and H plus atom to balance the hydrogen atom. Okay, now you have to add water molecules to balance the hydrogen and oxygen atom. Okay, here you have 7 oxygen. So you want 7 H2O molecules. If you have 7 H2O molecules, you have total 14 hydrogens. So add 14 hydrogens on the left hand side. So you have balanced oxygen as well as hydrogen. Now add electrons on the side of the half reaction to balance charges. If need to make the number of electrons equal in the two half reactions by multiplying one or both half reactions by appropriate number. Okay, now the oxidation half reaction is thus rewritten to balance the charge. Now you have to balance the charge. Here you have plus 2, here you have plus 3. Now if you want to make it plus 2, you have to subtract one electron from this end. So Fe plus 3 plus electron is removed. Now the reduction half reaction are net 12 positive charges on the left and the side, only 6 positive charges on the right hand side. Now therefore we add 6 electrons on the left hand side. Now overall you can see there is 6 electrons on the reduction half, whereas 12 electrons on the reduction half and 6 reactions on the oxidation half. Sorry, 6 on the reduction half you have 12 positive charges, whereas on oxidation side you have only 6. So you have to add 6 electrons. Okay, so you have to multiply them by 6, overall by 6. So you will have 12. So now we will rewrite the equation. Okay, here if we rewrite the equation, what will happen is first this reaction, second this reaction. So it will be 6Fe2 plus giving 6Fe3 plus 6 electrons. Okay, then second reaction, Cr2O7 2 minus plus 14 hydrogen plus 6 electrons giving rise to 2 chromium 3 plus 7H2O. Now here these 6 electrons will cancel out, so it will become 6Fe2 plus Cr2O7 14 hydrogens giving rise to 6Fe3 plus 2 Cr3 plus and 7H2O. Overall the reaction is balanced. Okay. The seventh step is to verify the equation containing same type of number of atoms and same charges on both the sides of the equation. Last step is to cross check whether there is equal number of atoms on both of the sides and equal number of charges on the both of the sides. We will solve more examples of this and you will understand more of them. We will finish the chapter first and then I will have one more video added where we will solving all the balancing of redox reactions. Okay. Now, next is the redox reaction as the basis for titration. Now in acid base system we come across with a titration method for finding out the strength of one solution against the other using a pH sensitive indicator. Now, in titration what we do, we titrate acid against base or base against acid using an appropriate pH indicator. We add a indicator to that, right? There is a change from colorless to pink to colorless. Yes or no? That is what we do in titration. Now, similarly, in redox system, in titration method can be adopted to determine the strength of reductant or oxidant using redox sensitive indicator. Now, for redox reaction also you can carry out a titration, and this titration will determine the strength of your reductant or oxidant, how strongly it can reduce or how strongly it can oxidize. Now using a redox sensitive indicator. Now this usage indicators in redox titration is illustrated below. Now how you can do that? The first step is, in one situation the reagent itself is intensely colored. Okay, in one reaction you can see the reagent itself is darkly colored. For example, your permanganate solution. Permanganate means potassium permanganate, KMnO4 solution. Here KMnO4 acts as the self indicator. Since it is highly colored, it acts as a self indicator. Okay, the visible endpoint in this case is achieved after the last of the reductant, that is Fe or C2O4 2 minus is oxidized and the first lasting tinge of pink color appears at MnO4 concentration as low as 10 raised to minus 6 moles per decimeter or 10 raised to minus 6 moles per liter. Now, how you will see the end point? End point is achieved when the last reductant, last amount of reductant is also oxidized and the first lasting tinge of pink color appears at the MnO4 concentration. That means that dark purple color is converted into a pink color. So the first lasting tinge of pink color, the drop which will convert that purple into a lasting pink color. Okay, and this ensures a minimal overshoot in color beyond the equivalence point, the point where the reductant and oxidant are equal in terms of their molar stoichiometry. Now, this ensures the minimal overshoot. Minimal overshoot means the color beyond the equivalence point. So, if the drop converts the dark purple color into pink color, that means at that point your reductant and oxidant are equal in terms of their mole stoichiometry. Okay. Now, second thing is, if there is no dramatic autocolor change, as with MnO4 titration, there are indicators which are oxidized immediately after the last bit of reactant is consumed, producing a dramatic color change. Now, for KMnO4, it is a self-indicator, but those redox reactions where there is nothing like KMnO4 or there is nothing like a self-indicator, you add an indicator, external indicator to that, and that indicator will change its color the moment the last bit of reductant or last bit of molecule is oxidized immediately, producing a dramatic color change. Okay, now the best example is offered in your potassium dichromate, which is not a self-indicator but oxidizes the indicator substance diphenylamine just after the equivalence point is produced, an intense blue color, thus signaling the end point. So in potassium dichromate, you add a self-indicator. It is not a self-indicator. Okay, potassium dichromate is not a self-indicator. You add a indicator called as diphenylamine. Okay, diphenylamine is the indicator used in potassium dichromate titration. Here what happens, the moment the last bit of molecule is oxidized, the diphenylamine indicator converts its color into dark blue, intense blue color, signaling the end point. That means you have attained the equivalence. Your amount of reductant and your amount of oxidant is equal. Okay. Now, there is yet another method. Okay. One is self-indicator, other one is you are adding an indicator. Yet there is another method which is interesting and quite common. This method is interesting and it is quite common. Its use is to restrict to those reagents which are able to oxidize iodine ions. For say example, copper. Okay, copper iodine. Copper, when you combine with iodine, you get cuprous iodide and iodine. This method relies on the fact that iodine itself gives an intense blue color with starch and has a very specific reaction with thiosulfate ions, which too is a redox reaction. Now here what will happen, I hope you will be doing this experiment. We have to take a solution, you have to add iodine to that, and to that you have to add a starch solution and keep it in dark for 5 minutes. What will happen is that iodine ka color will change into an intense orange color, but the moment you start titrating it against thiosulfide ions, you will get an intense blue color. Okay, now iodine, though insoluble in water, remains solution containing Ki and Ki3 plus. Ki3. On addition of starch, after the liberation of iodine from the reactions U2 plus ions on iodine ions, an intense blue color appears. This color disappears as soon as iodine is consumed by thiosulfate ion. So when you add iodine to copper sulfate solution, it will give you a intense yellowish color. The moment you add starch and keep it in the dark, it will give you an intense blue color. Okay, once you attain that blue color, take out the flask and start titrating it against thiosulfate solution. The moment the thiosulfate solution consumes all the iodine molecule, it will turn that intense blue color solution into a colorless solution, indicating the end point. Okay, so this is another form of redox reaction. So 3 methods we have seen. One, using self-indicator. Okay, the molecule itself acts as a self-indicator. Second one is when you add an external indicator. Third one is when you add iodine as an indicator. Now, limitation of concept of oxidation number. Now, as you observed in the above discussion, the concept of redox processes has been evolving with time. So as time is going, we are evolving new and new redox methods. Now this process of evolution is continuing. In fact, in recent past, the oxidation processes is visualized as a decrease in electron density, and reduction process as increase in electron density around the atoms involved in reaction. So in recent years, we have seen that oxidation, it is a process of decreasing electrons around an atom, and reduction is increasing electron density around an atom. Okay, so there are limitations of concept of oxidation number. You cannot follow one method because there are new methods which are still being developed. Okay, now redox reactions and electrode processes. The experiment corresponding to the reaction can also be observed in zinc rod is dipped in electrode sulfate solution. Now, during the introduction part, I have told you that redox reactions are also used in batteries. Yes or no? And about that in detail you will be learning in your 12th standard. Okay, but here you have a small concept called redox reaction and electrode processes. Now, when you have an experiment. In that experiment, you have two rods, zinc rods and copper rod. First, take zinc rod. You have to take zinc rod, dip it in copper sulfate solution. Now, the redox reaction takes place, and during the reaction, zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to direct transfer of electrons from zinc to copper ions. Now, when you have in this experiment, what you have done, you have taken a beaker, you have dipped zinc rod, okay, zinc rod into copper sulfate solution, CuSO4. Now, if copper sulfate you divide, okay, it will give you Cu2 plus ions. Yes or no? Cu2 plus ions. Now, what happens is when you start the process, the zinc rod, okay, in the zinc rod you have zinc, right? So the zinc will be converted from, zinc is oxidized from zinc to zinc ion, Zn to Zn2 plus. That means it is releasing 2 electrons, okay, Zn to Zn2 plus, releasing 2 electrons. Now this 2 electrons which are released, they are taken up by copper 2 plus ions, and they convert copper ions into metallic copper. Okay, now this is the direct transfer of electrons from zinc to copper ions. Now during this reaction, heat is also evolved. So in this reaction, heat is also evolved. So it is an exothermic process. Now we modify the experiment in such a manner that for the same redox reaction, transfer of electron takes place indirectly. Now here the copper sulfate solution is in same place, that rod is also in the same place, so it is a direct transfer. Now we will rearrange the experiment in such a manner that there is an indirect transfer of electrons. Now this necessitates the separation of zinc metal from copper sulfate solution. So in this case we are separating zinc metal from the copper sulfate solution. Now we take copper sulfate solution in a beaker and put a copper strip or rod in it. So you take a copper sulfate solution, dip a copper rod in it. We also take a zinc sulfate solution in another beaker and dip a zinc rod in it. Okay, so in short you have to take 2 beakers. Okay, you have to take 2 beakers. This will contain copper sulfate solution and copper rod. This will contain zinc sulfate solution and zinc rod. Now the reaction takes place in either of the beakers, and at the interface of the metal and its salt solution in each beaker, both the reduced and the oxidized form of the same species are present. So now what will happen? The reaction will take place in both the beakers, and at the interface of the metal you can have a salt solution. Okay, now here you will have a reduced and oxidized form of same species present. Now, this represents the species in the reduction and oxidation half reaction. Now here you will show the two reactions. One beaker will show a reduction, other beaker will show a oxidation. So a redox couple is defined as having together the oxidized and reduced form of a substance taking part in an oxidation and reduction half reactions. So here a redox couple is formed, which means you have an oxidation half reaction and a reduction half reactions. This is represented by separating the oxidized form from the reduced form by a vertical line or a slash representing an interface. So here you have to, or here you will represent them by separating them using a slash or a vertical line. Okay, so here you will show a reduction half reaction, here you will show an oxidation half reaction. You will separate them by a slash. For example, in this experiment, two redox couples. Okay, here you have two redox couples are represented, that is zinc iron to zinc and copper iron to copper. Okay, now in both cases oxidized form is put before the reduced form. So whenever you write that reaction, you will put oxidation first and then reduction. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side. So both the reactions you have to put side by side. Now we connect solution into beakers by a salt bridge, a U-tube containing solution of potassium chloride or ammonium nitrate, usually solidified by boiling with agar-agar and later cooled by jelly-like substances. Now here in this you can see this U-shaped tube. This is called salt bridge, and this salt bridge is formed using either ammonium sulfate or potassium chloride. What you have to do is you have to put potassium chloride into agar solution. Agar is a solution which forms jelly kind of substance. You have to add them in agar. When it is hot, agar is like a liquid. The moment you add them into that U-shaped tube and keep it for cooling, once it cools down, it becomes jelly like. Okay, so you have to put a U-tube, connect both the solution. One beaker you have zinc sulfate solution and zinc rod, other you have copper sulfate solution and copper rod, and both of them are connected by the U-tube. Now this provides an electrical contact between two solutions without allowing them to mix with each other. Now this U-tube will connect them with an electrical connection, but there won't be mixing of the solutions. Okay, now the zinc and copper rods are connected by a metallic wire with the provision of an ammeter and a switch. Now you have to connect both the rods. Now you have connected both the solutions. Now you have to connect both the rods. Now both the rods are connected using a metallic wire. To that you will add a switch and an ammeter is provided. Now the setup shown is called as Daniell cell. Now this entire setup, okay, this is called as Daniell cell. Okay, this entire setup is called as Daniell cell. Now when the switch is in off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As you know, if the switch is off, there won't be any kind of reaction taking place. There won't be electrical or electric current passing through the metallic wire. But as soon as you put on the switch, okay, following things are observed. Okay, the moment you put on the switch, the transfer of electrons now does not take place directly from zinc to copper, but through the metallic wire connecting the two rods, as is apparent from the arrow which indicates the flow of current. Now initially, first experiment, what happened, you had taken copper sulfate solution, in that you have dipped zinc rod, right? So the electron transfer taking place was direct, but here there is no direct electron transfer. What happens is, the moment you put on the switch, the electrons will start generating here and it will start moving from one rod to other rod through this metallic wire. So this is the flow of current. In this direction is the current flowing, and this direction is the flow of electron. Okay, now the electricity from solution in one beaker to solution in other beaker flows by the migration of ions through salt bridge. Now the electricity which is formed, it is balanced by the flow of ions through the salt bridge. So excess of ions which are formed, they are transferred into other beakers using this salt bridge. From here the electrons are migrated. Now we know that the flow of current is possible only if there is a potential difference between the copper and the zinc rods known as electrodes. Okay, so the electric current, the flow of electric current is possible if there is a potential difference, if there is a difference between the copper and the zinc rods called as the electrodes. Okay, they are called as electrodes. Now the potential difference associated with electrodes is known as electrode potential. Okay, so the potential associated with the electrodes is known as electrode potential. If the concentration of each species taking part in the electrode reaction is unity, if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure, and further the reaction is carried out at 298 Kelvin, then the potential of each electrode is said to be standard electrode potential. Now what is standard electrode potential? When the concentration of each species taking part in the electrode is in unity, that means if I have 1 mole of solution in both the beakers, okay, both the beakers I have 1 mole of solution, and the pressure on both the beakers is 1 atmosphere, and the temperature or the further reaction carried out at the temperature of 298 Kelvin, okay, it is a standard electrode potential. That means everything is in standard, equal number of electrodes or equal number of concentration. For example, I have 1 mole of concentration, 1 atmospheric pressure, and 298 Kelvin is the temperature. If all these three, that is concentration, pressure and temperature, if all these three I keep it equal, I maintain it at same amount, that time the potential that is produced on electrode is called as standard electrode potential. By the convention, the standard electrode potential, that is E naught of hydrogen electrode, is 0 volts. So for hydrogen the standard electrode potential is 0. The electrode potential value for each electrode process is measure of the relative tendency of the active species in the process to remain in the oxidized or reduced form. Now what is standard electrode potential or electrode potential value? It means it is the electrode process, okay, is a measure of relative tendency. Okay, it is a tendency of the electrodes to either remain in oxidized form or reduced form. Okay, a tendency of the electrodes to remain oxidized or to remain reduced. Now a negative E naught means that the redox couple is stronger. So if you have a negative electrode potential, that means your redox couple or the reaction is stronger, or the reducing agent than the H plus H2 couple. Okay, now a positive electrode potential means your redox couple is weaker reducing agent. Okay, so negative means stronger reducing agent, positive means weaker reducing agent. The standard electrode potential are very important, and we can get lot of other useful information from them. So standard electrode potential is very important, as you can get lot of information from them. The values of standard electrode potential for some selected electrode processes are given in the table. So here, and you will learn more about electrode reactions and cells in your class 12th in electrochemistry chapter. So this is the electrode potential values. Okay, this is the electrode potential values of some of the chosen electrodes. Okay, here you can have 0. Okay, so this is the increasing strength of reducing agent. Down is your increasing strength of reducing agent. Top is your increasing strength of oxidizing agent. So these are highly oxidizing agent and these are highly reducing agents. Okay, so with this we are done with the redox reactions. I hope you have understood. So thank you for watching my video. Please do like, share and subscribe.